All right, guys. So continue from the previous video. After you have determined if there's conjugation or not, okay, the next related skill is to determine if a lone pair can move or delocalize, which means because it's conjugated, right? Or it cannot move, localize, stay at the same place. All right. From the previous video, we talked about that the lone pair adjacent to a double bond, they can be parallel with the two double bonds here, not two p orbitals here. So it is delocalized. You can draw the curved arrow there, right, and draw out the another resonance structures. Now, the lone pair right here, is this lone pair conjugated with this double bond? Not really. Right, this not really. Look at this double bond here. Okay, so this double bond, the orbital of this, the orbital of this lone pair is sticking out of that carbon is already on the double bond. No ways that this carbon can arrange itself that make the orbital with the lone pair parallel with the two p orbitals on here. It's right. So my point is, the lone pair on an sp2 carbon is localized. It cannot move. You cannot draw any arrow right there and you get a resonance structure. It doesn't make any sense. Okay. All right. Come down here. Look at this lone pair right here. Just one of them. There are three total. Just one. Right. Is that lone pair delocalized? It is. This is a lone pair adjacent to double bond. So that lone pair next to double bond. Lone pair next to double bond. Right. Lone pair next to double bond. Now look at right here. So this lone pair, that lone pair can be parallel with these four p orbitals. Okay, so you can draw the resonance structure there. Draw the curved arrow. All right, and this guy right here. Let's see what happens. So that one of the lone pair. Now just take one of the lone pair. Is that lone pair delocalized? No, not really. Here's the problem. That carbon right there is an sp3 carbon. So there's no p orbitals in here that this lone pair can get in. Okay, so there's a breakup conjugation. So all these three lone pairs are localized. You can't draw anything on it. All right. All right. Lastly, that lone pair, is that lone pair delocalized? It's also localized. No, not delocalized. This is localized, right? If you still remember, the lone pair on an sp2 atom is localized. No way on earth that this lone pair right here, that lone pair right here, it can be parallel. Take a look. This one of this lone pair. This guy cannot be parallel with these four p orbitals because it's already on oxygen who's already participated in the conjugation. Okay, you can't draw any resonance structure there. All right. Okay. Let's try this. Okay, so you have to determine if a lone pair localized or delocalized. If it delocalized, you should be able to draw a curved arrow. Okay, start with this lone pair right here. Lone pair next to double bond. Of course, this is delocalized. All right. Now next one, a lone pair on an sp2 atom, totally localized. You can't move anything on it. Okay. All right. Next one, lone pair. Adjacent to double bond. Is that lone pair adjacent to double bond? This guy's localized. You can draw the resonance structures, right? Now, if this guy delocalized, the other one is not is localized. You can move only one of them. You can move both of them at the same time. Okay, so delocalized. This guy's localized. But if you pick this the lone pair on the right to be delocalized, you can draw the arrow. The lone pair on the left is localized. All right. Now, cinnamaldehyde. This lone pair right here are localized. Good. This is sp2 oxygen. Lone pairs on an sp2 atom is localized. All right, you can't move it. All right, oxygen is already participated in the conjugation. All right, these two lone pair cannot. This is the same thing. So lone pair on an sp2 nitrogen. Okay, an sp2 atom are localized. All right. Last one, retinol. Lone pair right here. Well, it would be localized if this carbon right here has is an sp2 carbon, but it's not. It's an sp3, no p orbital there. So these two lone pair are isolated from the conjugation right here. Okay, so these two are localized. All right, so it takes some time. This is just a lot of work in here, but with practice, you should be able to see localized, delocalized, lone pair, or conjugation, or non-conjugation. All right. All right. A little bit application of conjugation and localized or delocalized thing here. So all the markers or the colors that you see, the compound that give out this color, most of them are have a long conjugation. Look at this guy, the yellow color. It's just a lot of double bond, double, single, double, single, double. I mean, it's just a big conjugation there, and that cause itself to have color, right? We have blue, we have red. There's a lot of conjugation there, right? And there's pink. Another object or another substance that have color. For example, our blood, right? Look at our hemoglobin. Our blood is red, and hemoglobin, that's come from hemoglobin, which is red in color. Look at the conjugation: double, single, double, single, double, single. It's just a long conjugation there. And other animals that have their own blood and their own color. We have blue color. We have green for what's it? Leeches, worm, submarine worms, and we have violet. I never seen this violet before. Yeah, but there's a lot of conjugation there. Okay. Why does conjugation causes substance to have color? I'll let you learn that in, I think it's organic chemistry 2, or maybe next course. Okay. All right, we have chapter 2, class activity 2. So we have question 1, question 2, and question 3. All right.